know, and then there's like a whole debate. Check it out. Okay, so we are very happy to have Stefanos with us. Stefanos presented a paper that got accepted at ZKProof 6 and is going to give us an SoK, systematization of knowledge on what don't we know and topics about security. So, Stefanos, go ahead.
Thank you. So I don't want to be that guy, but I think one problem that we have to solve before starting deploying, and we have already deployed many systems using SNARKs, but there are still many security issues. So we have to solve also that problem before going forward with many more deployments. So this is a joint work with Jens, David, Theodore, David Wong, Mohammed, and Ben. So, how does it work? Okay, cool. Okay, so in this talk we will I will briefly speak about why should we care about ZKP vulnerabilities, what are the layers that issues can arise, what is the impact of vulnerability and which properties can be broken, what is the threat model for systems using SNARKs in production, and we will also present a taxonomy we did for ZKP vulnerabilities, and finally what we can do to prevent those issues. So currently the state of ZKP applications is ZK rollups, which at the moment have a TVL of around 4 billions. There is ZKs, as always has been there. There are many very interesting applications that arise, mostly in the infrastructure level, like ZK login presented by Kostas previously, ZK mail, ZK bridges, and also there are private programmable L1s and L2s, and finally there are many interesting off-chain applications that could happen. But what we haven't observed so far in that industry is exploits. And although there have been very critical vulnerabilities in deployed systems, like the counterfeiting in ZKs, another constraint issue in Tornado Cache, a vulnerability in the circuits of the ZK VM of ZK Syncera, and a bug in the verifier of a GNARC protocol. All those were either detected by people from within the protocols that designed and implemented those systems, or by white hackers that reported the vulnerability, or during audits. But nothing is exploited so far. And what I'm hearing as an argument about that is the complexity of those systems and those vulnerabilities. But here is one vulnerability in the circumlib from 2019. And I don't know how many people, so the green line is the fix, and the line above is the vulnerability. How many people could have detected this issue? No one? It's just a missed constraint, so maybe my hypothesis that those vulnerabilities are not that difficult, it's not correct. But as we will see, some of the ZK vulnerabilities, in my opinion, are kind of easy to detect and potentially easy to exploit. Some others are way more complex, though. So we tried to understand how easy or not is to detect those, but also exploit, because we have no exploit so far. So some efforts on doing a taxonomy for ZK vulnerabilities are the ZK bug tracker from 0xSpark, which they have 22 vulnerabilities by now. There was a talk in ZK Summit 7 where again they JP described some vulnerabilities there. And then this year there was a real nice talk in ZK Summit 11 where Yumin basically gave a presentation of how we can onboard Web3 auditors to audit ZKP protocols, and I really recommend all those presentations and the bug tracker. So what we try to do is to better understand what's going on and where things can go wrong. So let's first start with the layering we did and what is our understanding of systems that using zero-knowledge proofs. So first, you have a relation, a program, a statement that you want to prove. So you have to write a circuit. And this is the step that most bugs happen, when you go from what you want to prove to the actual implementation of the circuit. Then we have the front end. And in the front end, we typically have a compiler that processes the circuit and generates some constraints in an intermediate representation, in an arithmetization. And also we have the witness generator that also it's created typically from the circuit, and it gets the public and maybe some private input and produces some traces. And then we have the backend. Yeah, and in the backend we have three main functions: the setup function, the proving function, and the verification function. And in both these layers, that could be bugs that are basically infrastructure bugs. There could be bugs in the front end that when you compile something, you don't generate the constraints you thought they were going to generate it. And in the backend, there can be other issues that we'll see later. And the final layer is the application layer, which is the code that interacts with the SNARK. For example, in the blockchain space, this is typically a smart contract that will take some input, and it will take maybe some proof, and it will call the SNARK verifier. So if we add ZK VMs in that equation, then instead of circuit, now we have another circuit that is a ZK VM circuit, and typically the user then just has a program that feeds to the ZK VM along with the inputs. So another way to see that categorization is in a hierarchy, and here we have the semaphore protocol example, where we have solidity, then circum, then the circum coded circum and SNARK.js, which is the front end and the back end. Then we have some libraries that we might use for low-level mathematical operations. Then on the abstract layer, we have the proof system, right, which is the description of the proof system we want to implement in the backend, and we need to do some things with it in the front end. And then we have like our other software, hardware, runtime, whatever. In this work, we don't care about anything that is non-ZK related, but all the other traditional security issues as well very important for the deployments of those systems. The important thing I want you to get from that figure is that any issue in the lower levels could break everything you can build on top of it. So if someone finds a critical vulnerability in the SNARK we are using, then every implementation will be broken. If there is a bug in the front end or in the back end you are using and can be exploited, then all your circuits are broken. So the properties we have and the reason why we are using zero-knowledge proofs are knowledge soundness, perfect completeness, and zero knowledge. I think those are pretty well defined already. So let's move on to our thread model. So I want you to think about it from one easy example is from the perspective of ZK rollups in their current form, right? We have the network adversary, which is basically someone that can observe public inputs, proofs, and everything. Maybe he can find a malleability attack by that information. Maybe he can exploit it or not. Then we have an adversarial user. This user actually can submit some inputs to our systems in case of the ZK rollups to the L2, and then we consider that the prover is non-malicious. And this is not the threat model we want to use in ZKP applications, most probably. But this is what we have in many of the deployments at the moment, but this would change. The adversarial we want to be safe against is the adversarial prover that has the ability to produce and submit proofs. So he can exploit any bug that might happen in any part of our stack. Maybe another more advanced adversarial is if also has access to some part of the trusted setup ceremony. And in our paper, we provide a table where we describe all the capabilities of different adversaries, and you can find more there. So what is the impact of ZK vulnerabilities? First, we have the most severe, which is breaking the soundness, which means a prover can convince a verifier of a false statement. Then we have breaking of completeness, which means that we either cannot verify or even produce a proof for a valid statement. And finally, we have breaking zero knowledge, which basically means that we have some information leakage. Now, what we did is we picked 141 bugs, and we found those bugs through audit reports. We looked more than 100 audit reports. We found those bugs through vulnerability disclosures, like the ones I saw in the beginning of this talk, and we also searched for critical vulnerabilities in bug trackers of open source systems. We did not consider any non-ZKP related vulnerabilities here. So for example, in the audit report there was a re-entrance vulnerability, we skipped that. And here is a table with a high-level overview of our results. So the columns are the layers and how many vulnerabilities were in each layer. And then we have the impact of each vulnerability. So the main layer that has the most bugs is the circuit layer. That doesn't mean that the other layers do not have bugs, but probably people have not looked that much in the other layers. For example, most of the audits are on the circuit layer, so there might be more bugs in the front end or in the back ends that we don't even know. And it's pretty difficult to detect those bugs, actually. And the main impact of those vulnerabilities are soundness issues that it's really bad for the protocols. So why are there bugs in circuit layers? So when you write a circuit, you have to think about two things. First is computation, the computation part, and the second one is the constraints. And depending on the DSL you are using, you might have to write a circuit where everything is the same part of the code. So you have to specify all your computation and then to apply all the constraints you want. It might be something like a hello to circuit that you have a table that you fill with one function and then you assign your constraints with another on top of that table. But in general, it's not the simplest thing you have to do. And when speaking with people that are not that familiar with zero knowledge proofs, the way they are thinking about programs is computations, where the way you have to think about programs in zero knowledge proofs, in SNARKs, it's with constraints and then fill your computation. So we have observed that this is the main reason why we have so many bugs in the circuits. And the vulnerabilities we might have in the circuits are unconstrained issues where we missed some constraints or our constraints are correct, but there are some corner cases that might lead to soundness issues. We have over-constrained vulnerabilities that are not that common, and in that case you have more constraints than the one you needed, so you might reject some of the inputs and some of the computations. And then we have computational hints error, which is the case where basically the way you compute things is wrong. So that could lead to both soundness and completeness issues. And it's more like logic bugs in the code that the circuit is written. So we tried to identify root causes for the circuit layer. And basically the intuition is that, for example, in the second bullet point, because some constraints are complex or are very costly, people try to do optimizations. So the simplest optimization you can do, which someone can argue it's not even optimization, is to not check that your inputs are in the correct format you want, in the correct range you want, etc. And leave that to some other components that are going to call your circuit, or some code that will call the verifier, etc. And that could lead to many bugs. So this is the missing input constraints. Then in some cases, the constraints might be very complicated, and because some things you cannot written directly to circuits, you have to come up with smart tricks. So that can lead to many under constraint issues. And then the last of those three is the out-of-circuit computation, not being constrained. And what happens in that scenario is that you have some computation. Some part is very expensive. So you take some values outside of your circuit. You use some Rust code or some functions in Circom to do some computation, and then you need to reintroduce that value in the circuit and properly constrain it. And then we identify that there are many issues during that process. And in our paper, you can find a complete taxonomy about all those issues, and with some examples. Two very simple examples that most probably are not that visible. The first one is from Hello 2, and is the missing input constraint. And basically, one reinject was missed from that gadget, and that could lead to major vulnerabilities. And the other one is from a Circom circuit that was performing inside the circuit some signature verifications. And this is a very common pattern for many of the applications. It's from ZKBroof. And what they wanted to check is that the field elements, they're not using native field arithmetics, that the inputs are less than the prime of the BLS12. And to do that, they used the big less than circuit component. And although they have used it correctly, in the end, you still have to check that your inputs were not larger than the field. So the result of big less than is 1. And they didn't have that check. And that could lead to like basically completely broken signature verification. So the next layer in the integration layer. And here we identified 4 main vulnerability types. The first one is passing unchecked data. And this is the case when in the circuit we have some assumptions about the inputs. And we expect that the code that calls the verifier will enforce those assumptions, but the code unfortunately didn't. And then we have issues that can happen in proof delegation and proof composition. And finally, issues related to ZKP complementary logic. What we mean by that, the simplest example is nullifiers, where basically you have some logic, for example, in your smart contract or in your client contract, or in your client code about how to handle nullifiers, and you mess something up there, which is not directly a bug into your ZKPs, but it's pretty close. Here is the example of the bug in solidity, where basically you had to check that the nullifier is less than the SNARK field, because that's the assumption of the circuit, but you didn't, so your code can be exploited. And finally, there are various vulnerabilities that can happen in front-end and back-end. We didn't have that many of those in our dataset, so if you're aware of any that we might have missed, please send me those. And the main 2 issues in the front end is either in the witness generation or in the compilation pipeline, and actually there have been detected bugs there, where you have your circuit, and then you have your compiler that takes the circuit and produces the constraints, and basically the constraints the compiler produces are not equisatisfiable with what you defined in your circuit. And that could lead to severe soundness issues. And then in the backend, the most common issues are in the verifier, where either you have an error in the implementation of the verification algorithm, some arithmetic errors, or again, you missed some checks. One example is the bug found from the OpenZeppelin people in one audit in GNARC, and they're going to have a presentation about that later today. Finally, there have been already many efforts on developing and creating tools for detecting some of those bugs. So we have categorized them based on which layer they focus on and what kind of vulnerabilities they can detect. For example, circumspect is a linter for circum for finding under constraint issues. ZKApp is a static analysis tools. Then we have some formal verification tools. Again, mostly on the circum, or correct is on the Halo 2. We have some languages that apply some security formal methods to help users find bugs. And yeah, we also SNARK probe is a fuzzer. But what we can observe from here is that most of the tools work specifically on one DSL, and that's problematic. Some of the methodologies some of the methodologies can be applied to other DSLs, but the main issue we are observing so far is scalability issues. So with many of these tools, yeah, you can find the circum bug we showed in the first slide, but you cannot find more complicated issues because of the complexity of those circuits. So at least at the moment, those tools do not scale that well. And finally, we observe from the audit reports that some companies and some code bases using traditional security tools, for example, like AFL to find bugs in a backend or in a frontend, but this most probably cannot even solve the Oracle problem we have in testing for finding, for example, soundness vulnerabilities in those systems. And then there can be errors that can happen in the proof systems, and we didn't really explore and analyze those in our paper. Those are mostly cryptanalysis research, but there are two cases why that can happen. Firstly is because there are errors in the original description of a proof system, and secondly because there are incomplete descriptions. So it's up to the implementers of the proof system to define like which hash function they will use, for example, and that could lead to many issues. So, in conclusion, why do we have bugs? I think I can summarize what we found from that study in two quotes. The first one is that ZKPs are not just maths, there is implementation, and bugs in implementation can break all the properties we want to provide by using SNARKs. And the deeper you go in the layers we describe, then more things can be broken, and we should develop better methodologies for finding those issues. The second one is a quote that David Wong told me when we were working on our project, and it's basically a quote from Ron Rivest from for one of the proposals for the specification of digital signature schemes. And the quote is that the poor user is given enough rope with which to hang himself. And I think in ZKP, when we develop using SNARKs, the things are even worse because cryptography is exposed to the outer layer. So people can mess things in a very bad way. And in some cases, yeah, you have to work with cryptography in the outer layers. But in some other cases, people try to write very simple circuits that they shouldn't be aware about all the tiny details. Then, in many DSLs, we miss fundamental abstractions. Like in most DSLs, we don't have the notion of types. We just have fill elements. And that we observe it's a main issue why we have so many vulnerabilities in the circuit layer. Then there is a complexity when using SNARKs, and also there is a different threat model, especially for people that are not that familiar with SNARKs, and we have to educate them, and we have to be very clear on what the threat models should be. And the most important for me at the stage we are is that we have lack of specifications. And that goes from the lower layers, but also on the top layer. People start writing a circuit, and then they want to audit a circuit, and typically we don't have a clear picture of what the constraints should look like. So it's really important to start writing specifications, at least informal specifications. So what can we do? And basically it's the negation of all the previous points. So we need more learning resources. And I think already people spend time to writing blog posts, writing papers, doing research in finding new techniques for detecting those issues. We need to write specifications. And it's great that as a community we had a session about verification and formal verification in that space. But I feel the first step is specifications. And we need to really try to write specifications for everything that we implement in the field. And my intuition is that by just writing specifications, we don't even need to scale formal verification for most vulnerabilities. We will find it by just simply have the specifications. And then we need more easier and more secure programming languages to make it more accessible and secure to write programs that use SNARKs. And there are already great efforts towards that end. Noir and Leo are two great examples. And finally, we need in general better testing and security tooling. And that goes from testing frameworks to formal verification that, in my opinion, should be the end goal. I feel that for many of the DSLs, we don't even have like an infrastructure to easily run soundness, to easily run unit tests for finding soundness vulnerabilities. You have to do it manually. In most code bases, there are not even such unit tests, so that would lead to many vulnerabilities, and we could have prevented many vulnerabilities by doing that. So here is our paper, and it's public in archive, and you can read it. Thank you.
Any questions? All right.
So you said in the conclusion that one of the actions we could take was to provide more learning resources. I'm wondering if you have something more specific there, because I think there's a lot of tutorials and things like that on zero knowledge, right? So the question is, do we need more learning resources, or do we need better learning resources? And so, like, I guess, what is the requirement? What does success look like in this?
I think, for example, the two main books we have, right? It's a very nice start. It's for more advanced people, and it's for more difficult to deep dive, but that's a great start. Then I feel like the presentations I showed in the beginning are very useful to better understand the security issues. And then it's similar to specification, right? We need more documentation. We need to make clear that in CIRCOM, if you don't apply some specific constraints, there are issues. So, and we need to do that for everything. For example, when you create infrastructure for example, ZK mail, ZK regex, and such examples, you need documentation about how to use those things and what are the assumptions. And that goes from the top level of applications and libraries to the lower level. I think in the lower level, we have better specifications and documentations than in the upper levels, which is kind of weird.
Thanks for the presentation, Stefano. Have you tried to apply any large LLM to find attacks automatically? Because I personally found one on Blast. I mean, for 0 points, they had an issue, and this could actually put everything in the air, right? And a human probably cannot do it because this is a very low detail into the dependencies of the software that we're using, for example, to verify or prove something. I personally realized that, like, theory is one thing. We can find attacks on the theory, on the documentation, but many mistakes as a domino effect are going to the next and the next and the next use, and eventually we have some like very, very big situations of the whole community failing.
So if I get it correctly, the main question is if we have tried to use LLMs to find such issues in the whole stack. And the short answer is no. People have tried to do it in other fields, like smart contracts, that LLM should be much better because we don't have that many training data sets for LLMs for zero-knowledge proofs, right? The amount of CIRCOM code we have, it's much less than the amount of Solidity code we have and the bug reports we have for Solidity. And the results were not that great for Solidity, for example.
But did you try it?
Yeah, they have tried it. There are some papers, and yeah, the results are not that great.
You don't just want circumcode, you want good circumcode also.
Yeah. I would say that it will be probably worse, but I cannot prove that. We need to do it to prove it for zero-knowledge proofs because of the data that are out there, right?
Okay, thank you very much.